In this lecture, I have discussed about how the relay coordination is done for overcurrent relay for a substation. So let us take a simple example where a single line diagram has been shown for 132 by 33 kV substation. So in the 132 kV bus, the source fault MVA for the source is 1000 MVA, and two number of 50 MVA transformer is connected, which are running under parallel condition of percentage impedance of each 10%, and MVA capacity is 50 MVA. In the 33 kV bus, we have one bus coupler of CT ratio is 800 by 1, and two number of feeder is connected in each side of the bus coupler. So here the CT ratio for the HV side and LV side for the transformer is 400 by 1 and 1000 by 1. So from the CT secondary side, overcurrent relay is connected for the feeder, for the bus coupler, for the LV side of the transformer, and for the HV side of the transformer. So how the relay coordination is done for the overcurrent relay, I will discuss in this lecture. So what is the philosophy of relay coordination? The philosophy of the relay coordination is done based on the fault calculation. So I have considered two cases. Number one, for which the bus coupler breaker is on and two number of transformer are running in parallel condition. So in this case, fault occur at feeder 1 very close to the 33 kV bus. The fault current will be almost equal to the bus fault at 33 kV bus, and this fault current will be supplied by two number of transformer. So in this case, we have considered the trip time for the overcurrent relay for the feeder is t second or t millisecond, and for after some grading margin or time margin, this overcurrent relay will trip the circuit breaker of the bus coupler. Okay, so the fault is segregated between each section of the bus coupler. Now again, for the LV side of the transformer, again some grading margin has been given, which is 150 to 200 millisecond more that of the bus coupler overcurrent relay. Again in the HV side, the grading margin is another grading margin is given, which is again 150 to 200 millisecond. That is T3 is equal to T2 plus 150 to 200 millisecond time to be taken by the overcurrent relay to send a trip signal to the circuit breaker of the HV side of the transformer. So why the grading margin is given? For example, the fault occurs very close to the 33 kV bus at feeder 1. This fault current shall be cleared at T time by the relay which is connected from the CT secondary side of the feeder. If this relay is failed to clear this fault, then bus coupler relay shall send a trip signal to the circuit breaker of the bus coupler so that fault can be isolated. The healthy system should not interrupted. Here healthy feeder is feeder 2. So again, if this bus coupler breaker is so fault is isolated between each side of the bus coupler, the fault current will still persist from this one. So in this case, the relay which shall send the trip signal to the circuit breaker of the LV side of the transformer. So here the grading margin is given, that is T1 plus 150 to 200 millisecond. So T1 is the time which is taken by the overcurrent delay of the bus coupler. So if again another grading margin is given for the HV side of the overcurrent relay, which is T3, that is T2 plus 150 to 200 millisecond. So this is how the overcurrent relay coordination is done for case 1, that is both the transformer are running in parallel condition but bus coupler breaker is on. So in this case, I have considered the case 1, which is two number of transformer are running in parallel condition and bus coupler breaker is on. So we have to first calculate the fault current at 33 kV bus. So here the source fault MVA is 1000 MVA and base MVA I have considered as 100 MVA. So source impedance, that is ZS, is equal to kV square by MVA. here source is connected to 132 kV bus, so source impedance will be equal to 132 square divided by 1000, since fault MVA of the source is 1000 MVA, which comes as 17.424 ohm. So Z base, that is the base impedance at 132 kV system, will be equal to kV square by MVA, that is the base kV square divided by base MVA, which is given by 132 square divided by 100, since 100 MVA is considered as base MVA. So which comes as 174.24 ohm. So we can calculate the source impedance in terms of per unit value, which is given by Zs by Z base. So Zs is equal to 17.424 and Z base is equal to 174.24. So source impedance in terms of per unit value comes as 0.1 per unit. Now in case of transformer, the per unit or percentage impedance or per unit impedance is given as 10%, which is equal to zero point 0.1 per unit at its own base MVA, which is equal to 50 MVA base. So this base MVA, this percentage impedance or per unit impedance of the transformer, we have to convert in terms of the base MVA, which is considered as 100 MVA. So the formula for converting the per unit impedance in terms of new MVA base, which is given by ZT equal to 0.1. 0.1 is the per unit value of the impedance of the transformer into MVA base new to the MVA base old. So here the MVA new is 100 MVA and MVA old is 50. So the per unit value of the transformer in terms of 100 MVA base equal to 0.2 per unit. So the equivalent circuit can be drawn from the parameter which is converted to the common base value for the source impedance and the transformer. So source impedance is 1 per unit to the common base value 100 MVA base, and ZT is the transformer impedance value in terms of per unit value at common base, that is 100 MVA. So two number of transformers are running in parallel condition and fault occur at 33 kV bus. So we have to calculate the equivalent impedance, then we can calculate the value of the per unit value of the fault current at 33 kV bus. So this is the three-phase symmetrical fault current. So Z equivalent comes as Zs plus Zt equivalent. So ZT equivalent is 0.2, which is connected in parallel with 0.2. So here comes as 0.1. So Z equivalent comes as 0.1 plus 0.1, that is equal to 0.2 per unit. So fault current at 33 kV bus in terms of per unit comes as 1 divided by Z equivalent, which is equal to 1 divided by 0.2, which is equal to 5 per unit. So this is the value of the three-phase symmetrical fault at 33 kV bus. Now we have to calculate the value of the base current at 33 kV system. Since base MVA is considered as 100 MVA and base kV at 33 kV is 33 kV. So we can calculate the phase current of the base current at 33 kV system, which is equal to 100 divided by root 3, that is 1.732 into 33. So which comes as 1.75 kilo ampere. And fault current is given by at 33 kV system is per unit value of the base fault current into base current. So here the value of the per unit of the first fault current is 5 per unit and base current is 1.75 kilo ampere. So fault current comes as 8.75 kilo ampere. So if fault occur very close to the 33 kV bus at feeder 1 or 33 kV bus, this value of the fault current will be 8.75 kilo ampere, since two number of transformers are running in parallel condition. Now in this diagram we have shown the sharing of the fault current to the fault point. So the fault occur very close to the 33 kV bus at feeder 1. The value of the fault current is 8.75 kiloampere. So since the two number of transformers are running in parallel condition, equal share will be there by the two number of transformer. So the fault current will be supplied from the LV side of the transformer of each is 4.375 kiloampere. In the HV side, the reflection of the fault current will be 1/4 with that of the HV side, LV side current. So in the HV side, considering that the transformer are running in nominal tap condition, the current which will be supplied from the HV side of the transformer will be equal to 1/4 of 4.375 kiloampere, which is equal to 1.09375 kiloampere. So this fault current will be supplied from the source. So we have to calculate the value of the TMS for each of the overcurrent relay by considering a fixed time for the overcurrent relay for the feeder and grading margin of 200 millisecond from that feeder to the bus coupler and to the upstream of the circuit breaker. Okay. So here the trip time is considered as 200 millisecond and IDMT characteristics of the overcurrent relay IC standard inverse curve has been chosen for which the trip time is given by the formula trip time T is equal to 0.14 into TMS divided by PSM to the power 0.02 minus 1. So here TMS means time multiplier setting and PSM means flux setting multiplier, which is the ratio of the fault current to the current setting at the relay. So in this case, we have to calculate the value of the TMS for overcurrent relay, for the feeder, for the bus coupler, for the LV side of the transformer, for the HV side of the transformer. So for the feeder, we have considered the trip time as 200 milliseconds. So here the trip time is equal to 200 milliseconds. So TMS, that is the time multiplier setting for the overcurrent relay of the feeder, is 0.2 into PSM to the power 0.02 minus 1 divided by 0.14 as per the formula. So here the PSM is given by fault current divided by current setting. Here the current setting at the relay is 1 ampere in terms of the secondary value. So in terms of primary value, the current set is 400 ampere since the CT ratio is 400 by 1. So value of the PSM is equal to 21.875. So the TMS value comes as from this formula as 0.091 second. So value of the TMS for the overcurrent relay for the feeder is 0.091 second. So for the trip time to be 200 millisecond for maximum fault condition. Now we have to calculate the TMS setting for the bus coupler relay, which is connected from the CT secondary side of 800 by 1 of the bus coupler CT. So for this case, we have considered that value of the trip time as T1 is equal to 0.2 plus 0.2. So that is 200 millisecond time margin has been chosen for the bus coupler relay with respect to feeder. So here the trip time is given by 0.4 second or 400 millisecond. And PSM is the I fault divided by I set. Here the I set is 1 ampere in terms of the secondary value, or in terms of primary value it will be 800 ampere since the CT ratio is 800 by 1. For the bus coupler, the fault current will be supplied as a half of that of the fault current at feeder 1. So here the fault current which is supplied or sensed by the relay in terms of the primary value is 4.375 kiloampere. So here the PSM for the relay which is connected for the bus coupler end will be 4.375 into 1000 divided by 800. 800 is the current set in terms of primary value. So which comes as 5.46875. So value of the TMS, that is the time multiplier setting, is equal to 0.4 into PSM. PSM is 5.46875 to the power 0.02 minus 1 divided by 0.14. So value of the TMS comes as 0.098 second. So by choosing the grading margin of 200 millisecond, the value of the TMS comes as 0.098 second for the bus coupler overcurrent relay. Now again we'll calculate the value of the TMS for the overcurrent relay for the LV side of the transformer. Again some 200 millisecond grading margin has been chosen. So trip time comes as T1 plus 0.2, that is T1 the trip time of the overcurrent relay of the bus coupler, which is 0.4 plus grading margin, that is 0.2, which is equal to 0.6 second. So here the I set is 110% of the full load current of the LV side of the transformer. Since the capacity of the transformer is 50 MVA and full load current comes as 875 ampere, which is given by the formula 50 divided by root 3 into 33, which comes as 875 ampere in the full load current. So current set value in terms of the primary value is 1.1 into 875, which is equal to 962.3 ampere. So we can calculate the value of the PSM, since fault current which is supplied from the LV side of the transformer is 4.375 kiloampere and I set is known. So here the PSM value is given by 4375 divided by 962.3, that is the 110% of the LV side full load current. So value of the PSM comes as 4.55. So we can calculate the value of the TMS, which is given by zero point 0.6, that is the trip time for the LV side of the transformer, into PSM to the power 0.02, that is 4.55 to the power 0.02 minus 1 divided by 0.14, which comes as 0.132 second. So value of the TMS for the overcurrent relay, by considering that fault must be clear within 600 millisecond, comes as 0.132 second or 132 millisecond. Now we have to calculate the value of the TMS setting for the HV side of the transformer. Again we have chosen the grading margin as 200 millisecond. So here the trip time is given by T2 plus zero point 0.2, that is the T2 is 0.6 or 600 millisecond. So T3 comes as 800 millisecond or 0.8 second. Here again I set the current set in the relay over current relay is 110% of the full load current. In the HV side the full load current is 218.7 ampere, which is given by the formula 50 divided by root 3 into 132. So here the current set comes as 110% of the full load current in the HV side, which is equal to 240.6 ampere. So trip time, which is given by T3 equal to 0.14 into TMS divided by PSM to the power 0.02 minus 1. So we can calculate the value of the PSM, since the fault current is known and relay setting is known. So here the reflection of the fault current to the HV side of the transformer is 1.09375 kiloampere or 1093.75 ampere. So here the PSM value comes as fault current divided by current set. So fault current is 1093.75 ampere divided by current set, which is equal to 110% of the full load current, which comes as 240.6 ampere. So here the PSM comes as 4.55. So value of the PSM is same, since the fault current is supplied by the HV and LV side of the current, and current set is same for the LV side and HV side, that is the 110% of the full load current. So here the value of the TMS comes as 0.8, that is the trip time, into PSM to the power 0.02 minus 1. The value of the PSM is 4.55. So 4.55 to the power 0.02 minus 1 divided by 0.14, which comes as 0.176 second. So by considering the trip time as 800 millisecond, the value of the TMS for the HV side of the transformer is 0.176 second or 176 millisecond. Now let us summarize the value of the TMS for the overcurrent relay coordination by considering the trip time at feeder as 200 millisecond. So for feeder, the TMS value comes as 0.091 second, and for the bus coupler, the TMS value comes as 0.098 second, and for the LV side overcurrent relay of the transformer comes as 0.132 second, and for the HV side overcurrent relay comes as 0.176 second. So this is how the relay coordination is done when the condition is that both the transformer is running under parallel condition and bus coupler breaker is on, and maximum fault current is considered considering that fault occur at feeder which is very close to the 33 kV bus.